we have to be able to derive certain equations for moment of inertia and also center of mass. What we want to find out now is, let's go ahead and try to derive the equation for the moment of inertia about the center of mass for a uniform rod of length L and mass M. That's what we want to derive. Here's our rotational axis. Spinning around this axis, right, the 50 centimeter axis right there, spinning it around, what's the moment of inertia about this axis? So here's what we got to do. We have to, now this is a continuous object, it's density, it's linear mass density, lambda. Now that can be a constant for this uniformly dense rod, and in this case, lambda equals the mass, number of kilograms per unit length, and that is a constant for this rod because it's of uniform density. It could actually change density. In other words, the rod could get more dense as we go to one side. But let's deal with this simple case first. What we need to do is we have to add up all these little pieces of mass. And each little piece of mass, we're going to, I'm just going to pick out a random piece of mass here. This is an infinitesimal distance here, which I'm going to call, from there to there, is dx. That's dx wide, and it's a mass of dm. It's got an infinitesimal mass. Now, what our job is always going to be is trying to express this infinitesimal piece of mass, trying to express that in terms of this infinitesimal piece of distance, dx. That is almost always our job, to express dm in terms of dx. Well, this is not so bad for this one. Dm, this little piece of mass, is going to be equal to lambda times dx. If this is the x-axis right to left, how much mass does it have? Well, the linear mass density, how many kilograms per meter, is the same throughout this thing. So if we've got the number of kilograms per meter right here, that's the number of kilograms per meter. You multiply it by the number of meters, dx, and you get the number of kilograms. Of course, it's going to be infinitesimally small, but this equation still works. So I can express dm as lambda dx, and that's going to be really, really important for what I'm about to do. So here's the general equation for I. I is equal to the integral of r squared dm. Now compare this to, really, it's just the same thing as the sum over all I of mi ri squared, but here, instead of discrete masses m, I'm using little infinitesimal masses dm, and there's an infinite number of them. So really, it's kind of the same thing as we did before, but now we have to use it for infinite number of these things. So I'm going to re-express this, and now what is r going to range from? Notice that r, what is the maximum r value? Well, out here. But we got to be careful here, and in this situation, we actually have to use our number line. If I call this 0 distance, and I call this L over 2, I can't call that L over 2 because it's in the opposite direction. So I'm going to integrate this from r equals negative L over 2, that's right over here, to r equals L over 2. That's right over here. So that's how I'm going to integrate this whole thing. And in the middle, r is going to equal 0. So let's take a look at this, and I'm going to just draw a line right here so we can kind of keep that separate. All right. So I can only integrate this with respect to r. Really, my r is what I'm calling my x here. My r is in the x direction. So I'm just going to rewrite this as x squared dm from x equals negative L over 2 to x equals L over 2. I can do that because I'm just in the x direction. All of my r values are in the x direction. By the way, this rod is really infinitely thin. It has no height to it. It's just a one-dimensional rod that's L long. Now, once I get it to here, I can re-express this in terms of x. It's going to be from negative L over 2 to L over 2. X squared, what is dm? Well, we already found that right over here. That is times lambda dx. That's dm. And then I'm going to express this a little bit more specifically. Lambda we know. So again, the integral of negative L over 2 to L over 2 of x squared. Turns out that lambda, as we said before, is m over L. That's lambda. However many kilograms per unit length, that's a constant. And then it's going to be dx. So I can just take out that m over L. So m over L will come out as a constant. And then I'm going to integrate x squared dx. So here's what that's going to look like. I've got the integral of this part on the inside will be x cubed over 3. And I'm going to evaluate that from negative L over 2 to L over 2 right there. So here's what I'm going to evaluate right there. So it's m over L times, we got to do L over 2 quantity cubed. That'll give me L cubed over 2 cubed is 8, and that's over 3. Minus, final is, it'll be negative L cubed over 8, again over 3. And when you do this calculation, this gives us I about the center of mass is equal to, of our rod, is equal to m over L. This gives me 2L cubed over 24. And when we do that, we cancel one of these L's out. And that gives me 1/12 ml squared. So in other words, bottom line, I of a rod about, this is a uniform rod, about the center of mass is equal to 1/12 ml squared. Using the parallel axis theorem, you can figure out that about around one of the ends, it'll be 1/3 ml squared.